Okay, so hello everybody, and welcome to this lecture series on point set topology. So, I think that topology is one of the most fascinating areas of mathematics. It's extremely useful, and it finds applications in almost every area of mathematics. And point set topology is really the most fundamental type of topology. It's sort of like a doorway into the whole subject. It looks at things in very general terms, and some of the more specialized kinds of topological studies, like algebraic topology, really build upon point set topology. So let's just dive right in and start to discuss the subject. Now, there are quite a lot of definitions in point set topology, so I would like to be very clear about the different notation I'm going to be using. So I'm going to start by showing you some notation which you probably already know, but it won't take long and it's good to be clear about such things. So I'm going to write this to denote that A is a subset of B. So I use this symbol here to denote that something's a subset. And also I use this kind of two-way arrow here. You can think of this as meaning if and only if. The arrow to the right says that the statement on the left implies the statement on the right, and the arrow pointing to the left says that the statement on the right implies the statement on the left. Okay, another piece of notation I'm going to be using is 2 to the x. And what that means, this is equal to the set of all subsets of x, also known as the power set of x. Okay, so here's an example of using this 2 to the x notation. So if we have the set containing a and b, then the power set of that, which we write as 2 to the ab, will be the set which contains the empty set. It contains a and b and ab. And also I'm going to write this thing which kind of looks like a curly E to mean in. So this notation here just means that x is in the set A. Okay then, so I think that's all the notation I'm going to need for the time being. So now I can start talking about topology. So let's rub out all this stuff. Okay, so let's begin with a definition of a topological space. So let X be a non-empty set now. Tau, which is a collection of subsets of X, so we write it like this, is a topology on X if three conditions hold. So the first condition is that X itself and the empty set are both members of tau. So tau is just a collection of subsets of X, okay? So we require that X itself and the empty set are members. And our second requirement is that if S is a collection of members of tau, then the union of all of those members is also a member of tau. So the union of elements in the topology is also an element in the topology. And the third and final condition is that for any pair of elements in the topology, we have that the intersection of those elements is also a member of the topology. So we're using a little bit more notation here. So this symbol here, this cup, this means union, and here this says we're taking the union over members A of S, and this symbol here means intersection, this cap symbol. So when we have all these conditions, then that means that tau here is what we call a topology. This is a topology now. And in this case, we have that we say that X tau is a topological space. And also, a bit of sort of shorthand, we call the members of tau open sets. So these are really important. A topology is defined by the open sets, and there's if you have a given set, there's usually lots of ways that you can define open sets, and they often correspond to different kinds of topologies which you can have on something. So the way you define the open sets basically affects the kind of topology you have. So these open sets are really a very fundamental thing to the subject. Okay, so it turns out that there's an equivalent way of writing this third point here, which is fairly important. So we can also express this point 3 like this. The intersection of any finite subset of tau belongs to tau. So there we have it. Now, the reason that this is true is something which I'd like you to work out for yourself. So I strongly suggest you pause this video and see if you can show that this writing in blue here follows as a consequence from this statement 3 written in black. So if you want to pause the video now and try and work that out, you can do that, because I'm going to tell you the reasoning behind it now. So basically, you can prove this inductively because you know that the intersection of any pair of elements from tau of any pair of open sets is an open set. That's what this writing in black says here. And so then we know that the intersection of any two open sets is an open set, and then the intersection of any three open sets can be obtained by taking the intersection of two open sets and intersecting it with another open set. So then we get that the intersection of any three open sets is an open set. And then we can make any intersection of four open sets by taking the intersection of three open sets and intersecting it with another open set, and so on and so forth. So we can just go on by induction and show that for any finite number of open sets, their intersection is also going to be an open set. Now, it's an important thing to note that there is a little bit of asymmetry here, because statement 2 says that the union of any set of open sets is an open set, whereas statement 3 says that the intersection of any finite set of open sets is an open set. So there is a difference between these union and intersection operations and how they interplay with the concept of open sets, but it's slightly subtle. Okay then, so let's take a look at some important examples of topologies. So a very important example is what's called the discrete topology. So the discrete topology has a set of open sets equal to a set of all subsets. So tau equal to the power set of X is called the discrete topology. On a non-empty set X. Okay, so this is an important topological space. So we call X 2 to the X the discrete space. Of course, there are many discrete spaces, one for every set. Now, here's an important property of the discrete topology. We'll have it as our first proposition. Well, it's an important thing related to discrete topology. So, if we have a topological space, x tau, such that so if this is such that for every element of X, we have the set which just contains X is an open set. Then tau is the discrete topology. Okay, so that's our first proposition. If our topological space is such that every singleton is an open set, then that is the discrete topology. So I'd like you to pause the video again and see if you can prove this. Topology is definitely the kind of subject that you need to study the proofs of, and you need to think about it a lot. It's very difficult to learn unless you actually roll up your sleeves and try and prove some things for yourself. So I suggest you pause this video now and try and prove this. Okay, so the proof of this is as follows. We want to show that every subset of X is an open set. So let's just take some generic subset of X. And now we can write that as the union over all the elements of S of the singleton X. So that is equal to S. And since that's the union of open sets, by our point 2 in the definition of a topology, this is an open set. So there we have it. That's the end of the proof. Okay then, so let's take a look at another important topology. In particular, the topology which just involves the empty set and the set itself. So this is called the indiscrete topology. And it's defined on any non-empty set X. So it's called the indiscrete topology because it's really the opposite to the discrete topology, which has as many open sets as possible. The indiscrete topology has as few open sets as possible for a given non-empty set X. And so we call X tau the indiscrete space in this case. Okay, so I began discussing topology with the definition of open sets, and now I'm going to talk about the complementary concept of closed sets. So just as you can define a topology on a space in terms of open sets, you can also define it in terms of closed sets. And you'll see that there's a large amount of symmetry between the two things. So, in particular, we have that, well, let's let X tau be a topological space And now we have that a subset of S, a subset of X, is closed. We say it's closed when its complement is open. Okay, so it's a bit of new notation here. I'm writing this, which sort of looks like X minus S to denote the complement of S. So if you like, this is equal X minus S is equal to the set of all elements which are in X, but which are not in S. And some people write it like this. So we can have it as our definition of a closed set. But there's another way to express the closed sets in a topological space. And here's where you can see the symmetry, well, almost symmetry between open sets and closed sets. So maybe I shall just rub this out to make a bit more space. Okay then, so proposition 2. So we're going to be talking about the open sets now. So if X tau is a topological space, then we're going to have 3 properties holding. The empty sets and X itself are going to be closed sets. For each collection of open sets. Whoops. I meant to say the intersection of any collection of closed sets is closed. And finally, the union of any finite collection of closed sets is again closed. Okay, so how are we going to prove this result? This is a very important one. So the important thing to notice is that the closed sets are just complements of the open sets. So if you remember the definition of a topological space, we had it as part of our definition that the X itself is an open set. So if X is an open set, meaning that it's in tau, then that implies that the complement of X, which is equal to the empty set, is closed. And there we have it. So similarly, we also had as part of our definition that the empty set is an open set. And so then the complement of the empty set, which is equal to X itself, it must be a closed set. I just want to remark here that it is really confusing for when you first begin learning topology. The idea that closed sets are not the opposite of open sets. A set can be closed and open. It can be neither closed nor open. It can be open and not closed and not open. There's really no exclusivity at all going on here. Okay, so let's see if we can now prove part 2 of our proposition. So what we want to do now is to show that the intersection of any collection of closed sets is closed. So let's suppose that we've got a collection of closed sets. We'll call that collection A. So we have that each member S of A is closed. Okay, so what does that mean? Well, importantly, it means that the complement of S, since S is closed, the complement of S is open. And what that means is that if we take the union over all members S of A of X minus A, that's the union of a collection of open sets. And so by point 2 of our definition of a topological space, that is itself an open set. So we have that this thing here is open. Now, can we write this in a better form? Well, it can be written as X take away intersection S in A of S. Let's just check this. Okay, so if we look at the right hand side, we see that this is equal to all of the elements in X which don't belong to every single member of A. And you can see that that's the same thing that's on the right hand side. So yes, these two things are equal. So we have that X take away the intersection of all members of A here is an open set. Okay, so what this implies now is that the intersection of all S in A is going to be closed because its complement is open. That's the definition of a closed set. So this has now proved point 2 of our proposition. Okay, so maybe you would like to have a go at proving point 3. It's a very good exercise. If you do, you can pause the video now, but I'll just do the proof anyway. So we want to show now that the union of a finite collection of closed sets is closed. So let's suppose we've got some closed sets. And since we've only got a finite number of them, we can index them. S1, S2, all the way up to Sn. And so since these are closed sets, we have that their complements are going to be open. And so the thing is that now, by our modified statement 3 in our definition of topological spaces, we have that the intersection of a finite collection of open sets is itself open. So what that means is that if we just take the intersection of all of these things, then that's going to be open. Okay, and also it's important to notice that this is actually equal to X take away the union of all of these S1 up to Sn. So let's just check that. So to be a member of this set here at the top, a element has to not be a member of any Si. It can't be a member of any of these closed sets Si. And also exactly the same condition defines the elements of this second set down here. This is precisely the set of all elements of X which don't belong to any of these sets Si. So these two sets are the same, and so X take away the union over all these SIs is an open set. And so we have the S1 union S2 union Sn is closed. Why is it closed? Because its complement is open. So there we have it. We've proved proposition 2. So now let's talk about a somewhat more interesting kind of topology, which is called the finite closed topology. So let X be a non-empty set. So topology tau on X is called the finite closed topology. If the closed sets of X are X and all the finite subsets of X. Okay, so I'll leave it as an exercise to you to prove that this is indeed a topology. You can have a topology like this. Okay, so let's look at an example of a finite closed topology. So let's let this n here denote the set of positive integers. So now the closed sets. So let's consider the finite closed topology on n. So now the closed sets are going to be n itself and all of the finite subsets of n. So for example, 1 and the empty set, and 2, 3, 5. And there's going to be lots and lots of these finite subsets, which are going to be closed sets. So in this case, we're going to have that every finite set is closed, and every open set, well, every open set is going to have a complement which is finite. So every open set must be infinite, except the empty set. Also, note that not all infinite sets are going to be open. So in particular, consider the set of all even numbers. 2, 4, 6, ... Is that a closed set? No, it's not a closed set because it's an infinite set. Is it the complement of a closed set? No, because the complement of it is the set of all odd numbers, which is another infinite set. So here's an example of an infinite set which is neither closed nor open. Okay, so let me leave you with some important definitions and a problem to mull over. So in particular, if we have a topological space, x tau, then we say that it is T0, this is a definition, when for every pair of distinct points in X, we have that there is an open set which allows us to distinguish between A and B in the sense that either A belongs to S and B does not belong to S, B is outside S, or A is outside of S and B is inside S. So that's a T0 space. That's a certain kind of topological space. And another kind of topological space, well, we'll write the definition down here. So we say that X tau is a T1 space, or simply it's T1, if each singleton subset is closed. So for each member of X, the set which just contains X is closed. And then the problem is to show that if X tau is T1, then it is T0. So I'm not going to show you how to do that. You can look over this before the next lecture. Okay, so thank you for your attention.